Thank you, and thanks to the organizers for the invitation. Let me just set up the pointer. Okay, so this is joint work with Nikhil Bansal, who's also here, and this is some work which extends a known rounding algorithm that uses discrepancy techniques. We all know about integer programs. We want to optimize a linear function subject to linear constraints and integrality restrictions on the variables. These are very useful class of optimization problems, and many combinatorial optimization problems can be cast in this framework where the variables are just restricted to be 0 or 1. However, the problem in general is NP hard, and so we can't hope to solve it exactly. And since I'm talking about approximation, in this area, a major approach is to relax the integrality restriction and solve a linear program, which can be done in polynomial time. And then we want to round this fractional solution to an integral one. And in doing this, we want to say that the loss in the objective is going to be small. So this is a general recipe which gives us performance bounds on our algorithm and also runs in polynomial time. There are, however, many problems where even testing feasibility is NP hard. So even determining if there is an integer feasible solution to some system of linear inequalities is NP hard. And here again, we can use this approach. We relax the integrality restriction and we find a feasible fractional solution. And now we want to round it to an integer point which is nearby. But I said feasibility is itself NP hard. So what we do is we relax all the constraints and we attempt to find a nearby integral solution. So we go from this fractional solution x to an integer solution y, which is not going to lie in this starting polytope, but we are going to relax the constraints by a bounded amount. And in this case, we are concerned about getting a bound on what extent the constraint is violated. And in this talk, we'll look at additive violations. So this is what we'll discuss today. So next few slides, I'll give a few applications of rounding with violations. And then I'll discuss the previous rounding approaches and our new result. And in the more technical part of the talk, I'll first give an overview of the previous discrepancy rounding algorithm due to Lovett and Mecca. And then I'll present our new variant of this. The first application I want to talk about is combinatorial discrepancy. Here we are given a set system with a collection of elements, n elements, and subsets defined on these elements. And we want to find a bicoloring of these elements so that every set is as balanced as possible. So we want an equal number of pluses and minuses. So in this example, we have these three elements being colored, let's say -1, and the discrepancy of the set system is 1 because that's the worst imbalanced set. So we just want to minimize this maximum discrepancy. And we can cast this as an integer program. We just have one constraint for every subset in this collection, and we want all these x values to add up to 0, and these variables are in -1, 1. And of course, we relax it and there's a trivial LP solution. So there's nothing going on. So the all 0 solution is feasible. And what's known for this, for a long time, the best rounding algorithm was essentially just randomized rounding. So in this setting where you have a linear number of sets, if you just choose a sign for every variable independently with probability half, then you can show that the discrepancy is going to be at most square root of n log n. And there was a non-constructive result due to Spencer which showed that in this setting there exists a coloring which is at most a constant times square root of n. So it's better by the square root of log n factor. And for a long time that was non-constructive. And in a breakthrough result, Nikhil showed that you can achieve this discrepancy in polynomial time. And his algorithm was based on certain SDP ideas as well as random walks, and a few years later, Lovett and Mecca made it significantly simpler, at least in understanding, which was purely based on random walks. And that's the method we'll extend. There's another problem that fits in this framework and that has also been studied very widely. This is the degree bounded spanning tree problem. Here we are given a graph, undirected graph with costs on edges. And as in the usual minimum spanning tree problem, we want to find a spanning tree of minimum cost, but the twist is we have additional degree constraints on vertices. So for every vertex, there is some bound on the number of edges that we can choose incident to it. And it turns out that if we just set all these bounds to be 2, then the feasibility problem itself becomes NP hard. This is the Hamiltonian path problem. And so we can't hope to get usual approximation bounds. And what people have looked at is ensuring that you do find an integral spanning tree, but you violate this degree constraints by a small amount. So this has been extensively studied, and many people in this conference have worked on this as well. And the final result in this line of work is essentially an optimal approximation algorithm where you incur no loss in the cost relative to an optimum which does not violate any degree constraint, but your algorithm violates possibly every degree constraint by an additive 1. There's also a generalization of this problem, which is called the crossing spanning tree problem, where the setting is the same as before, but the bounds are now on arbitrary subsets of edges, no longer on just vertex degree bounds. And in this setting, the bounds are slightly worse. The error that we incur in these side constraints is something which depends on the sparsity of this constraint set. So and this will be an important parameter in the rest of the talk. So the sparsity is just going to be the maximum number of these side constraints which contains any edge. So if we look at the vertex degree constraints, then every edge appears in 2 constraints, one for its left endpoint and one for its right. So the sparsity in that setting would be 2. And in general, you can have arbitrary set of constraints, but what we would look at is the sparsity, which is the maximum number of occurrences of any edge on these side constraints. And there is a different kind of algorithm for this problem, which achieves a different bound, so where the additive violation is essentially square root of b times log of the number of constraints. So these two are very different algorithms, and their performance bounds are also very different. So either of them can be better than the other. There's another application. I won't talk about this in depth. So this is low congestion routing, where you have edge capacity constraints. And here again, you want to find a solution that exactly satisfies certain constraints and possibly violates certain others. And again, it has a similar kind of story. There is one algorithm that achieves an additive sparsity type of violation, and another one that achieves an additive square root of b, where b is this right-hand side. Yeah. I see, it's a d minus 1. So this is also a similar story to the crossing spanning tree problem. We have 2 different algorithms that achieve 2 different kinds of bounds. So this is the talk, setting for the rest of the talk. We have a set packing instance, so a collection of elements and some subsets on them. And we have bounds on how many elements we can pick from each subset, and a parameter that we will be interested in, as in the previous 2 cases, is this maximum degree, which is just the maximum number of subsets that contain any element. And our results are interesting in the regime where these bounds B are fairly large. So in the talk, I'm going to assume that the bounds are at least log n. What's known here? Yeah, equality. We'll get 2-sided error. So the additive violation will be plus or minus. So the simplest rounding algorithm here is just randomized rounding. And that achieves a violation bound which scales as square root of b times log m. So b is the right-hand side of the constraint, and the next few slides are going to show the violation bounds as a function of this right-hand side b. So if we have a constraint that has a right-hand side of log m, that's the additive violation. If we have a constraint that has right-hand side of n, then the additive violation is square root of n log n. So this is just randomized rounding analyzed using Chernoff bounds. And a better version of this, still randomized rounding, but now which works in multiple phases and analyzed cleverly using the Lowa's local lemma, was done by Aravind and later Layton et al. And this gets a sharper bound where the deviation is square root of b times log d. D is the sparsity parameter, the number of subsets that any element lies in. And there is a different algorithm using iterative techniques where you can achieve an additive violation of d minus 1. And the recent discrepancy-based rounding algorithm I mentioned gives also an additive violation of square root d times log n. And again, in general, d and square root d log n are not comparable, but our results are going to be interesting in the regime where this is smaller. So that's the way I've drawn it. And one thing I want to point out with these two results is that their violation bounds when b is quite small can be much worse than the multiplicative type of bounds that we get using Chernoff or the Lowa's local lemma. And the other thing is that these are multi-criteria problems because there are many constraints that we want to bound the violations on. So we can't simply take the minimum of all of these. It's not like these are all the approximation guarantees of different algorithms and we cannot just take the best solution because there's no easy way to compare two different solutions. One solution does well on one constraint and the other may do well on the other constraint. So that's our new result. We don't get the best of all worlds, but we get somewhat close. So we match the Lowit-Mecca algorithm always. So we are never going to be worse than the square root of d times log n. And in the lower regimes, we are slightly worse than what you can get using Chernoff bounds, and even worse than what you could get using Arvind's approaches. So we are always going to be smaller than square root of b times log n and square root of d times log n. And we can also handle for free any matroid constraint. So if you want to find a base in any matroid polytope subject to some arbitrary set of constraints, if you have these kind of sparsity patterns in the right-hand side of B, then we can get the same violation bounds on the side constraint and we will still find a base in the matroid. So this captures, for example, the crossing spanning tree problem in the low congestion routing problems. Okay, so next I'll give an overview of the Lowit-Mecca algorithm. So here we are starting with a fractional solution that satisfies a number of linear constraints. And we are given a target violation value for every constraint, some value c, so that we want to violate this constraint by no more than an additive c times square root of s, where s is the size of that subset. And this algorithm finds in polynomial time a partially integral solution where at least half the variables are going to get set to 0 or 1, and we'll ensure that the violation is no more than this for every constraint. And it's a randomized algorithm, so the first property will be in expectation. And by using an iterative procedure on top of this and cleverly choosing these parameters c, we can ensure that we find a fully integral solution that has a violation of at most square root d times log n in all the constraints. So how does this algorithm work? So this is the target polytope that we want to stay in. So for each constraint, we expand its boundaries by that amount from the fractional solution x, and we want to be between 0 and 1. And the algorithm is quite simple to state. We choose some really small parameter epsilon, 1 over polynomial in n, and starting at any point, which is initially the fractional solution, we're going to look at all the constraints of this polytope which are tight. And we'll be we'll ensure that we stay in the tight faces, and in that tight subspace, we are going to pick a standard Gaussian and move an epsilon amount in that direction. And whenever we reach another tight constraint, we stay in that subspace. So that's a picture. So you start from the fractional solution, you keep taking these random Gaussian steps, and you perform this for 1 over epsilon squared iterations, which is polynomial. And the claim is that at the end of this, you satisfy the 2 properties I mentioned before. So it's clear that we are never going to violate the constraints by more than this, because that was by design. We are going to stay inside this polytope. So the question is, why are half the variables integral in expectation? And we'll do this in 2 steps. We'll show that not many of these violation type constraints can get tight. On the other hand, a lot of total constraints will get tight. So the only remaining type of constraints are the integrality ones, so a lot of those should get tight. So why should there be not too many degree violation type constraints that get tight? If we look at this process from the point of view of any constraint S, then what's happening in each step is a zero mean process, and the variance we can show is going to be at most epsilon squared times the number of elements in this particular constraint. And we are performing 1 over epsilon squared steps, so using standard concentration inequalities, we can show that the probability that you're more than c times the standard deviation is at most e to the minus c square. And just by union bound over all the constraints, we get that the expected number of these deviation constraints that will get tight is at most some small fraction of n. Now, what about the other side? This is based on a nice potential argument. We look at this potential function, which is the sum of squares of all the variables. And notice that because we are bounded between 0 and 1, this is always a value between 0 and n. And in one step, what happens to this potential? The expected increase in this potential can be shown to be at least epsilon squared times the dimension of the subspace that we are in. So that's the expected one step increase. And so if we add it over all the 1 over or some constant over epsilon squared steps, then we'll find that the expected potential at the end is at least 2 times the dimension at the end, because the dimension of the tight subspace can only decrease as we go along, and the dimension of the tight subspace at the end is exactly the number of variables minus the number of tight deviation constraints minus the number of tight integrality constraints. So we know that the final potential is pretty large in terms of this, but it can never go above n, so this gives us a bound on the total number of tight integrality constraints. So this is Lovett-Meca, and in the next few minutes I'll outline our modification to achieve these multiplicative type of bounds. So we are in the same setting. I've just restated the Lovett-Meca result here, and all we want to do is get a sharper bound on this. We want to replace the square root of s term by a square root of b, where I just want to point out that b is always at most s, because we are in 0, 1. So we want to get a sharper bound here, and as before, we can use essentially the same setting of these parameter c's and an iterative procedure to find a fully integral solution that has that kind of a violation bound. So it will be the better of square root d and square root b. Okay, so this is based on 3 simple ideas, and I won't go into a lot of detail. So the first one is, if we look at the Lovett-Meca algorithm, we were modifying the point by taking a random Gaussian in every step. And now there's no way we can control the variance of that to be dependent on the current solution x. So the natural idea is to scale down these steps and move only a distance proportional to xi in dimension I. So then we can do the same analysis as before, and if we look at what's happening for constraint s, the mean is still 0, and this time we can bound the variance by epsilon squared times b, which is the right hand side, instead of epsilon squared times s. So this is exactly the type of dependence we want, and using concentration inequalities and our assumption on these summation e to the minus c squares, we can again get that the total number of tight deviation constraints is a small fraction of n. But there is a problem with this, which is that now variables are not going to reach the boundary 0 or 1 fast enough, because we've scaled them all down by x. So a lot of them could be close to 0. So that's not good enough. So one way we can try to handle it is enforce some notion of artificial progress and say that if we look at any variable that is very close to 0 or very close to 1, we just want it to stay within some range which is proportional to that. And then if the variable reaches either end of this boundary, we claim that we have progressed to the next phase. This variable has been rounded from this scale to the next scale. So that's what we do. If we are around 2 to the minus k, our scale will be around that. If we are around 1 minus 2 to the minus k, our scale will be around that. So this is good for one part of it, but then the issue is, what if most of the variables reach the wrong end? So only one end is integral. Earlier both ends were integral and we were making progress, but now maybe we found that most of the variables in this class reach the fractional end. And to fix this, we add a number of equality constraints, which will ensure that not too many variables go to the fractional end. And we say that for each scale, the total fractional value of variables in that scale remains fixed compared to the starting fractional solution. So if you have too many variables reaching the fractional end, then you should also have a proportional number of variables reaching 0 or 1. So it's a symmetric kind of process, and that's the constraint we throw in. And we are not messing up the overall process because there is only one constraint for every scale, and there are only log n scales. So we can enforce these constraints at equality and still get the rest of the argument. So I have 2 minutes. Maybe I'll mention what extra ideas we need for the matroid constraints. So this is the setting. We have a matroid polytope, and we have these additional linear constraints. And we want to satisfy the matroid base constraints exactly and violate these side constraints by a small amount. So the first issue is that the rank constraints are exponential, but this is a very well exploited idea by now. If we look at any fractional point in the matroid polytope, we can show that the subspace of tight constraints has low dimension. And if I'm going to assume that every point is strictly fractional, then we can show that the subspace of tight constraints has dimension at most n over 2. So this allows us to handle the matroid constraints as before, because we could ensure that the side constraints are not violated by assuming a slightly stronger conditions on that expression summation of e to the c square. And so in total, we'll still be able to say that we make adequate progress in each step, and we can find a partially integral solution. So there's one implementation detail that I didn't talk about in the talk, which is that the Lovett-Mecca algorithm was implemented using near tight constraints, that if you ever got even somewhat close to a constraint, they would freeze it. But that's an issue for us when we handle matroid constraints, is while we do know that the dimension of exactly tight matroid constraints is small, we don't know, at least it may be a true fact, but we just don't know such a result. What is a dimension of the near tight set of matroid rank constraints for an arbitrary fractional solution? We don't have any bound on that. So we really have to work with exactly tight matroid constraints, and that leads to certain extra technical details. We have to truncate the random walk at some steps, but that doesn't affect the rest of the analysis too much. To summarize, we get an algorithm that gets benefits of both randomized rounding and discrepancy-based algorithms. We still have a slight loss with respect to the randomized rounding algorithms, a polylog factor loss. And these results also extend to handle for free any matroid-based constraints. And it's a good question to see if we can handle other type of constraints with these deviations. So we don't know. There are results ruling out some of these things because there are integrality gaps, but you could still formulate a question which we could try to address, but we don't know how to handle it. Roughly, like the matroid we could handle for free because that's extra only n over 2 dimension of constraints, but with matroid intersection, that's the first thing to break down. We don't know, yeah. Right. Yeah, so the one thing is that's not sensitive again to the x, so it'll give us, right, so it's possible that something like that could work, but the other thing with the matroid polytopes is he needs this bound on the volume of the polytope. So with matroid polytopes you can have much less than exponential volume. So that's another reason that it may not work directly.